All right. So the last time we were talking about model-based navigation. There is one correction which was pointed out, that the LiDAR does use time of flight apparently, and I was clearly wrong or misinformed in that. So yes, it is using time of flight in order to determine the location of the different points in the point cloud which it returns. But I'm still very surprised as to how the time gap being so small can still yield a precise location of the point. So we need to really be able to measure precisely on the time in order to get the estimate of where the points are. But it seems to be the way that it is being done, and I was clearly not informed about it. So clearly that's a new information. We all have learned something. Okay, let's go back. So we were talking last time about model-based navigation systems, where we were discussing about what are the different sensors on a marine craft, and we were looking at what are the different sensors and how do they work. We are getting some qualitative information about these different sensors. We particularly looked at the GNSS position and what are the different constellations, which are the countries which are in charge of these constellations, and how do you ensure that you're getting a good position log. And we looked at some couple of ideas about differential GNSS and carrier differential GNSS. And you understood the idea that real-time kinematic really refers to the carrier-based GNSS signal, and only when the conditions are right, you'll be able to get a precise estimate of the position. So any changes in that environmental conditions, may deteriorate your carrier-based GNSS signal. Typically, differential GNSS is much more robust as compared to the carrier-based differential GNSS. So you can get up to 1 meter accuracy well with a differential GNSS system. But if you want a further more accuracy, it really depends on what are the environmental conditions in which you are operating. I didn't really talk much about this integer ambiguity n. It's not very much relevant for our course. If you're really designing GNSS systems and you want to really develop your own real-time kinematic system from scratch, that is where these things will be useful. For most of the applications that we are interested in, we'll be looking at commercially available systems. So we won't be dealing with those. So that's why I'm not going to cover that in too much detail in our course. We won't practically need them for our purposes. Okay, but if you are really interested, you can take a look at your textbook that has some information on it, but then this seems to be an open area of research as of now. Okay, then we looked at the idea of compass. We talked about magnetic compass and gyro compasses and how the difference between magnetic compass and gyro compasses exists. And I think some of you pointed out and showed me a good video on the WhatsApp group, which I was hoping to post on the Moodle, but since everybody now has access, there is no further need for it. So the advantage of these gyro compasses is that you do not require, they are not sensitive to magnetic, magnetic variations or ferromagnetic variations nearby, and they operate independent of the magnetic principle. So it allows us to operate it on ships which are made out of steel and without any much issue. Then we talked about this idea of wave filtering. We were looking at this idea that we want to really make sure that whatever we are measuring from our sensors will contain both low frequency and wave frequency components. But when we want to feed back signals into our feedback loop, we want to ensure that the wave frequencies are eliminated and only the low frequency stuff is passed down. So our controller should only take action based on the low frequency based motions. It should not try to react to the wave frequency components, because that would lead to a lot of wear and tear. And sometimes it's also possible that we may not be able to respond. The ship may be too large, or the inertia might be too large, that even though the actuators are trying to respond, It's like I'm trying to turn the rudder left and right very quickly, but really it doesn't make any change on the ship's heading that quickly. So these things have to be kept in consideration, so for which we need to make sure that the wave components are filtered out. So we talked about it qualitatively, and we understood that some operations require us to work with low frequency motions and some operations require us to work with wave frequency motions. So we looked at some ideas like active heave compensation, which really requires us to figure out what is the wave frequency motion which we want to compensate for. Okay, so we'll now focus our efforts more on wave filtering today. We'll understand how to mathematically bring in these filterings so that whatever measurements we are getting in, we should be able to separate it out into the wave frequency and the low frequency based components. Since we are looking at a dynamic positioning problem for most of our course, we'll focus on trying to get the low frequency stuff more accurately and less bother about what is happening with the wave frequency stuff. So we want to kind of eliminate the wave frequency stuff. That is our idea. So a simplest way to go about it is to look at what are called low pass filters. So the idea here is that our measurement y of s can be thought of as a combination of two things. So for example, let's say I'm measuring the heading angle of the vessel. I can think of this as coming due to two components. One which is coming due to the rudder dynamics, which should be basically the low frequency stuff. And then there is the wave components, which is coming as the wave frequency components. Okay, so if you look at it, the input to the system for this low frequency motion is the rudder angle. The rudder angle is basically denoting how we are going to control the vessel. But when it comes to the wave frequency stuff, we know that it is controlled actually by our wave elevation. Now, you can actually try to model the wave elevation and then try to use your RAOs to determine what is the first order wave motion. But for practical purposes, what we are primarily interested in is to get this wave frequency signal to be modeled in some other way. So if you look at it, the idea is that you can think of this wave frequency component as if it is coming from a second order differential equation, which is being given as an input to a Gaussian white noise. Now notice that that's not precisely correct, because we know that the waves in the ocean do not have a white noise spectrum. Okay, they have a spectra which looks like a Pearson-Moskowitz spectrum or a John-Swab spectrum, and that's very different than a white noise. But from a modeling perspective, I can think of it as some white noise being transformed by some filter so that I get the same response which I am seeing from the typical ship. Because at the end of the day, I want to eliminate this anyway. So from a modeling perspective, my interest is to, because I'm not really measuring this quantity, right? I'm actually measuring y of s. I want to eliminate whatever is there in that psi w of s. Okay, so I can think of it notionally as a second order differential equation being fed in with a white noise, which will give me the so-called response spectrum of my system. So let me kind of maybe make this a little bit more clear. Let's see. Okay, so typically what happens, let's talk about what really happens. You generally have the wave elevation spectrum, which looks something like that, correct? And any sea state can actually be gotten by discretizing this wave spectrum into bars. And at each of these omega, okay, basically I figure out what is the amplitude. 2 times s of that becomes my amplitude of that wave. And then I simply superimpose them to get my total wave elevation. where n is the number of discretizations. This is an omega n, let us say. So I have ai cos omega I t plus epsilon I, something like that. This you should have seen in either in your statics and dynamics course, or you should have seen in ship motions course. One of those two you must have definitely seen it. Okay. Now, when I say white noise, how is that different from the spectrum here? What does the white noise spectrum look like?
All frequencies same.
All frequencies are excited by similar energy, which means that I'm kind of going to see a flat line here. Okay, that line should be flat and straight. Sorry, yeah. So it should look something like that, which means at every different frequency, I have equal amount of energy in the system. Right? But that's not what a wave spectrum looks like, right? So that's definitely not the same as this. So this is not equal to as eta of omega. But then what am I doing here? So let's try to understand. I am taking this eta and separating it out into its different frequency components. And for each frequency component, I am measuring what is the motion. So let us say I have psi of t, which is the yaw angle. Then there will be a yaw RAO, right? Which I'll denote here as the C6. Okay, so let's say this is my yaw RAO. Okay, how would this yaw RAO look like? How would it look like? Any ideas? For a typical ship.
It will have a peak at the natural frequency of the, of the ship, right?
Yes, it will have a natural frequency. It will have a peak at some point, and then what will happen?
It will gradually decrease to its extent. I think for omega equal to 0, it will be 1 or 0.
It will be 1 or 0.
So,
is there a stiffness in yaw?
No, it's not. Yeah, it's 0.
So if I have a 0 frequency wave, then it should basically not yaw as much. It should start off at 0, right? If it has stiffness, so it should start off something like that and then go and probably might do some funny behavior like this. Okay, that's the typical RAO curve. Give me 1 second, let me try to find the RAO curve for the KCS. I should have it here. Okay, RAOs. Or let us say I'm looking at 0 degrees. 0 degrees RAO. Okay, so let us say 45 degrees. Okay, now let me try to, you're not able to see this, right? I'm sharing a window, not my screen. Okay, are you able to see this now?
Yes, sir.
So what we are seeing here is the RAO for the yaw for the KCS vessel at the full scale level. Okay, so that's why you are kind of seeing this range of frequencies between 0 and 1.5 radians per second. And this has been computed using our hydrodynamic code, which we have developed in our group called Hydro. This was trying to compare between VAMIT, Hydra, and another code called MDL Hydro-D, just to validate that whether we are seeing the same effect as others or not. So you will see that there's a peak, as I said, and then at very low frequencies, the RAO will keep rising up because of the idea that this is an angle. So at very low frequencies, we are basically dividing by a very small amplitude, which is why this will start going up. And because there is no stiffness. If there was stiffness, then this should have stabilized ideally at value 1, which is what you will see, especially if you look at the surge or the, heave RAO. So let me see. So this is the heave RAO. So you'll see that that starts off at 1 and then it decreases as the number of frequencies is increasing. So this is only telling you that when the frequency is very high, what is happening there? The system is unable to respond. So the wave is of very high frequency, but the ship cannot be excited in that motion. That's what it's telling you. Is that making sense? Yes. So similarly in the yaw as well, it's telling you that as the wave frequency is increasing sufficiently high, my ship's inertia is so big or so huge that we're not going to see much motion occur. So there is this so-called sweet spot of frequencies in which this peak is occurring. That's where you're trying to see the maximum yaw which will come about. Okay, so given that is done, let me come back to sharing my application. So you'll kind of see a graph which looks something like this for the yaw. So if I wanted to calculate the yaw motion for this wave elevation, what is our typical approach? What do we do? Anand, what do we do?
What should we calculate, sir?
I want to calculate the yaw angle for a particular wave elevation. How do I go about it? If I know the RAO, then what do I do? You took statics and dynamics as yet?
Yes, sir.
So this must have been covered there, wasn't it?
Yes, sir. I forgot RAO concept.
What is an RAO?
Response amplitude
What does it indicate?
indicates that like for a particular frequency, how much the ship will, how much it will respond.
Correct, precisely. So if I have a unit amplitude of wave at say this frequency, I need to observe a yaw angle which will correspond to this angle. That's what it means, right? So if I want to now compute for the wave elevation which is shown here, what is the response? What is the yaw angle for this wave elevation? How do I go about it?
Fine. Multiply it by frequency.
Multiply the time series by?
Frequency.
We multiply the time series by frequency? Think about it. Krishnavelu, what do you think? How will we get the yaw angle from the wave elevation? Krishnavelu, can you hear me? Yeah, how do you think we'll get the wave elevation, from the wave elevation, the yaw angle?
I can't remember exactly.
Can't remember exactly? All right, Vallabh? How will we get the yaw angle time history from the wave elevation?
So we know in the frequency domain we know it.
Mhm.
We can have it in time domain as well, and then for every small sections of it, we know what components of frequencies are giving what amplitude. So we can integrate.
So we exactly know these are the amplitudes and these are the frequencies. I have n of them, right?
Yeah.
N omegas and n amplitudes. What do I do next?
We have the RAO, like what frequency what gives what amplitude. We know that.
Correct. So for each frequency, I'll basically figure out what is this value. Correct? And then what do I do?
We have it in frequency domain, so we can convert it to time domain as well.
So how do I go about it?
Take the Fourier transform, inverse Fourier.
I take the inverse Fourier transform. No. There is something missing. I know originally this has a time history, correct? Correct? From there, we are determining what are the different n omegas and n amplitudes which will and phases. N of these phases will determine by taking a Fourier transform. Okay, so now I have n amplitudes, n frequencies, and n phases on my hand. Now what do I do next?
So like each of these frequencies, we know what at like unit amplitude of those what like the response is for each of these frequencies.
Correct. We know for each of these frequencies, omega I, where is my pointer? For I is equal to 1, 2, 3 up till n. For unit amplitude wave of frequency omega I, what will be the response? This is what that we know.
Yeah.
Okay. Now what do we do?
So we multiply it by the actual amplitude of those frequencies that we have in the.
Okay. So we are basically now doing zeta 6 of omega I times AI. Okay.
So,
All right. And then what we are doing?
so that is giving us the uh, the actual response coming from this wave.
This is the amplitude of the response coming from the ith wave.
Yeah.
Hmm.
So summing all of them, we should have the actual.
No, but this is only the amplitude. I still
Yeah,
not.
that cos omega I.
Yeah.
Plus.
So what do I have to do there?
It should it have cos of omega I t plus, because it'll be responding similar to the wave, right? So it'll have the same frequency as the wave, but I'm not sure about the phase difference.
So how will we account for the phase difference? Oh, this is the problem I should give you guys. I didn't realize there was this much confusion in this. Okay, basically when you take a Fourier transform, you are getting it as this, right? Let me come back and write it here. Eta of t is summation I equal to 1 to n ai times cosine of omega I times t plus epsilon I, let's say. The same thing can be written as summation I equal to 1 to n capital AI times e to the power, or I'll kind of write it like this, real part of ai e to the power I omega I t. Okay, where ai is nothing but ai times e to the power I epsilon I. Is this making sense so far? Are you confident that when I put this value of ai here, I'll get this expressions, these two expressions are the same.
Yes, sir.
Right? Now, basically now what am I seeing? When you take a FFT, when you take a FFT of this eta, what you get are these amplitudes actually. Okay, so you're not getting just the amplitude information, it kind of has amplitude and phase, which means it's a complex quantity which you're getting out. Okay, so now that I have this complex quantity and I know the RAO at all of these quantities, which itself is also complex, right? Because this is half of the story. This is only the modulus of it. There is another graph which will show you what is the phase of it. Right? So that amplitude and phase combined will give you a complex quantity. The RAO is actually a complex quantity which encodes not only, so it is basically telling me not just if I give an input amplitude of so and so of unit amplitude wave, what is the output response? But it is also telling me that if the input amplitude wave was a cosine wave, how much lag is there in the yaw time series which comes by? So if, let's say the wave is a cos omega t, the yaw angle time history need not be psi a times cosine of omega t. It will be sine a times cosine of omega t plus some angle, which means that there is some phase difference. What does that mean? So if I look at the time history of wave elevation, if that looks like this, then the yaw angle need not look like that. It might look something slightly different. There might be a phase difference. Okay? So the peaks do not align. And what is that difference in the peaks is the phase difference, which is also encoded in the RAO. All right, so RAO is telling me both those informations at once. Okay, now if we come back to our original idea, okay, now I know what are these different amplitudes, zeta 6 of omega I. I know that. What do I do now? I multiply that by my phase angle. Okay, once I know these because these I am able to get from FFT. These are coming from FFT, fast Fourier transform of eta of t. So once I know these amplitudes, I can read off from these two graphs what are the corresponding values of the RAO at each of these different frequencies, find them out, and multiply them with each of these individual amplitudes. So now this is just still an amplitude, right? What I'm seeing here is still just an amplitude. It has phase information also there, but it's not a time series as yet. Right? So to make it a time series, what do I have to do?
Inverse Fourier transform.
Sorry?
The inverse Fourier transform would give the time 6 then.
You can simply multiply this by e to the power I omega I t.
Oh, okay. Yeah. Okay. So that, yes.
Now that becomes a time history.
Okay.
Right? But again, we are interested in real signals. So we take real component of this. And that becomes you basically add this all up from I equal to 1 to n. And that becomes your yaw angle. The same process you have to follow whether it is heave, surge, sway, whatever it is. The same approach. Tell me this is clear. I didn't realize this was such a gray spot.
So not quite clear for me. This,
Tell me what is not clear.
so this expression that we got, psi of t, what does it represent? Like for a given spectrum of waves, how will the yaw angle vary?
No, this is telling me for a given wave elevation. So suppose I gave you a time history of the wave, which looks something like this, let us say. For that wave, I want you to find out what the yaw angle time history looks like.
So now the wave that you draw, that is having certain frequencies and certain amplitudes.
Yes.
So okay, so all of that, if we combine, we'll get it psi of t.
Clear or still not clear? Don't hesitate. This is a very fundamental principle which needs to be really clear in order to really appreciate what we want to do later on. So convince yourself that this is correct.
So that eta of t, that is having n frequencies, n omega i's, n ai's.
Correct. It is basically composed of these Fourier signals.
Okay, so that can be represented by a real part of this.
Correct. Still confused on what aspect?
Not confused actually. I just want to remember the procedure, what we did, how we came here.
Okay. Go ahead, summarize it for all of us.
Okay, so for a given wave elevation history, eta of t, it will contain certain frequencies, omega I. It will contain n frequencies. It will contain n amplitudes and n phases.
Correct.
That can be written in a complex form.
Correct.
Now,
so these are basically now complex amplitudes which you now know.
Complex amplitudes. Now that is all in frequency domain.
Yes.
Now we will multiply the RAO to it. Then that will give us the
amplitude domain for yaw angle.
Response amplitude in frequency domain.
Correct.
And that can be converted to time domain using we can do direct Fourier transform also, right? Inverse Fourier transform.
Yes, this is what is inverse Fourier transform. There's no difference.
E raised to I omega t. Yeah.
This thing of me multiplying by this is essentially inverse Fourier transform.
Yes. Then we can get the time domain of the response amplitude.
So then we can get the real signal out. Is that clear for everybody? Still see some confusion on some faces. Krishnavelu, clear?
It means yaw or AO multiplied with amplitude of the real part of the wave amplitude.
Not real, complex part of the wave amplitude.
Yes,
This
sir.
has real and phase both.
Okay. Then we get a setting angle of the.
Then we get the complex amplitude for our yaw angle, which we take a inverse Fourier transform, consider only the real part of it.
Okay, sir.
Anant?
Sir, where are we multiplying the RAO here, sir?
This is the RAO.
Okay.
We are basically reading off of the RAO at certain frequencies of interest to us, and at those frequencies we are multiplying that with the wave amplitude, because RAO represents for a unit amplitude of a wave what is the response, right? So if the amplitude is AI, then I have to multiply by AI in order to get the actual response.
Sir, basically, so that term contains both the amplitude as well as the phase that
Which
comes
one?
with the RAO. For
In the RAO, yeah, this is a complex value.
yeah, okay.
This is complex. Really that difficult? I thought this was supposed to be like simple. Okay, all right. We'll try to do a demo next time. Okay, to see this in action in MATLAB, or maybe I should just put it part of your assignment. But it was part of your assignment, especially for those who took ship structures. You did all of this. It was a part of your assignment. The project actually had it. You did much more complex things there. I'm surprised that how that is, the retention is not there. Okay, so now everything is clear so far. So that is the regular approach where given a wave elevation, how would I find the yaw time history or heave time history or pitch time history? Doesn't matter, whichever time history, I'll take that corresponding RAO and do the same process. Okay. Now, the problem here is that when I am trying to get our measurements out and I want to just represent this transfer function between eta of t to this, right? So psi of psi by eta at certain frequencies, that is nothing but my so-called RAO. And that is what we are using in this process to get from the wave elevation to the yaw time history. But I can also model the same thing in a slightly different way. Not as accurate. This is the most accurate way. That is the actual thing which is happening in the ocean. But for my purposes, I can consider it as if I am feeding some signal to a second order differential equation. And out of it, I should get this response. Statistically. That's what I'm trying to say. What am I saying here? So the idea now here is, so let us say, go back and see, look at this fellow. This transfer function is what I am presuming is going to give me a wave elevation spectrum, a quantity yaw angle spectrum, let us say, for a particular case. All right, so let me write that down. KW times S. So this H wave KW times S square plus is there a KW times omega 0? It is KW times S. Okay, so assuming that my psi W of S is given by H wave of S times W of S, where this is white noise. What is the corresponding differential equation? What is the corresponding differential equation which is relating the differential equation for psi W of S? We simply substitute it here, nothing very complex. And from this we know that psi W double dot plus 2 zeta omega naught psi W dot plus omega naught square psi W is KW times W dot of S. I'm not quite sure whether this W dot should exist. Is white noise, Brownian motion. Yeah, that is okay. That's kind of right. Okay. So this is the differential equation which is governing. I am saying that rather than go through all of this effort where I have to model eta first from a spectrum I have to take a spectrum, discretize it, find my amplitudes, construct eta, from that find out what is the different wave components, do this process to get psi of t. Rather than do that, I can assume that I'm feeding some white noise to some system which looks something like this, and it emulates the same behavior. I'm approximating it. The reason why I want to do this approximation is all of this modeling it accurately is not going to yield anything for me. At the end of the day, I want that wave frequency component to be gone. I want to remove it. So from a modeling perspective, I can imagine it to be some sort of a what you call transfer function which has a peak at somewhere close to the peak of the spectrum. So if you think of it, once I take this RAO and I multiply by the wave elevation spectrum, I usually get my response spectrum, right? And that response spectrum might look something like that, because I'm basically multiplying this fellow. That is my pointer. Yeah, multiplying this fellow by this fellow. Correct? Come on, don't stare at me like that. You guys are scaring me.
Yeah, that is in the initial case, right? The original case where we have the history, like where we have the graph of the wave elevations with respect to frequency. But in our case, for the assumption, we are using white noise and an REO spectrum that is like given by a second order difference frequency.
Correct. So basically, if I want to look at the so-called RAO, then I have the RAO is expecting an input in terms of a wave elevation. But I'm saying that I'll approximate the system as a different system which takes as an input just white noise and tries to give me the same characteristics of the system. So at the end of the day, whatever is my okay, I messed up here. Okay, this one. Whatever is my response spectrum for the yaw, I want that same response spectrum to be output by this system which I am showing here. And basically my point is I'm going to adjust my omega 0 and zeta in such a manner that it somewhat represents closely what is going on in the real case. I don't need to be exact, because this is things which I want to discard anyway. From a modeling perspective, I can understand it as if I feed a white noise to a second order differential equation system, I'll get a response which looks something like this. Is everybody with me so far? I'm still seeing some gloomy faces. Tell me what's not clear.
Can you repeat this part? Why do we want? Why do we not use the actual?
The actual one requires a lot of effort from my side. I need to know the RAOs. I need to know the what you call precise geometry of the vessel. I need to run a potential theory code to get my RAOs. I need to know the wave elevation. I need to know what spectrum it is following. Only then I will be able to model what is the wave component of it. Isn't it?
So yeah. So here you are just using modeling your own zeta and omega naught, and then you are
assuming that I'll just get it. So for example, let us say that I gave you a ship and I didn't give you all its CAD model and other things. Okay, but I asked you to, okay, you need to now eliminate all the wave frequency components. Okay, so in that case, what you'll have to do, you'll do some measurements, right? You'll measure what the yaw angle looks like over some time. And then basically, you may not know the wave elevation also. I may not be measuring wave elevation as well. I may only give you the yaw time history, but I want to model that as if it is coming from an output of a second order system. Okay, by adjusting zeta and omega n, I will basically adjust this transfer function. So if I look at the transfer function for this fellow, whatever we have here, this guy is the transfer function. If I substitute S is equal to I omega, right? That just simply gives me the so-called response amplitude operator for this system.
So we want this our custom made to be more or less similar to the original one.
Yeah, so that we can approximate it and go ahead with our job. We need not give a precise estimate. That's the point. We can take a rough estimate and go ahead with it, because at the end of the day, we are more interested in the low frequency stuff. So we are just modeling it in some way. I can think of it as if it is coming from some sort of a measurement. So if I wanted to, so suppose that you are in the actual field, let us say, okay, I gave you a ship and you're standing on top of the ship, and the ship is experiencing some motion in yaw. Because of your sensor, you are able to measure that yaw motion. Okay, you get that yaw motion time history, take a Fourier transform of it, and you plot it. You will see something going on in the low frequency stuff, and then something going on in the wave frequency regime. Now, whatever is going on in the wave frequency regime, I'll just simply try to ad hocly tune my zeta and omega 0 such that I am able to capture that dynamics. I don't need a precise modeling of what is happening with my wave elevation.
Yes.
Everybody following me? So I don't need to go through the full process. Now, you can't be on the ship and then decide, okay, I need the geometry of the ship, I need to create a mesh, I need to push this into Hydra, I need to specify the wave elevation, and then only I'll figure out what is the wave components of the yaw angle. I'm simply making a measurement and trying to fit a simple second order filter to it and say that this represents roughly my wave elevation. Okay? Still unclear? Tell me what is unclear. I'm just approximating the ideal way to calculate what is the, what you call, the ideal way one would go about is to model is, so suppose I'm measuring these values. Put a new page here. Yeah. So let's say I am measuring the yaw time history. Okay, so rather than thinking of that yaw time history is being composed of some low frequency stuff plus a wave frequency stuff, where this wave frequency, in order to determine this, I need to use the geometry of the vessel, I need to know the wave elevation at that site. Instead of going through all that process, I'm simply going to say that rather than that, this comes from a second order filter. Where I simply tune my zeta and omega 0 to more or less match what the spectrum looks like. That's all. Because this is a component which I want to eliminate at the end of the day.
So we are actually seeing this yaw time history.
Correct. Like your sensor, you'll actually be seeing the yaw time history. You'll actually be measuring the combination of these two.
Yeah, but we will be subtracting something, and that something is second order system that we are assuming the wave time part of it.
Precisely, you have now got it. Rather than think of the complete modeling of the wave elevation and then think of how this exact wave time history has come about, I'll simply say this rest of the part is coming from a second order filter. That is stuff which I want to get rid of anyway. I am really interested in the low frequency motion at the end of the day.
How do we know that we have done the, like, removed it properly? Like,
good question. I'm coming to that. At least once we have a basic understanding that if you're able to understand that I can represent this as a second order system, okay, then basically you now know that for any second order system, for a spring mass damper system, you know that the RAO looks like this, right? It starts off at 1, goes up, and then goes down, something like that. Right? For any typical second order system. Now, if I want this one to match the so-called actual thing, then I can tune my omega 0 so that I can shift this peak this way or that way, and I can tune my zeta value to tune how high this overshoot is. Okay, this is not really overshoot. What is the resonance peak value? I can tune it and get a representative value of this zeta and omega n, and I can assume that that's roughly the model. See, at the end of the day, you want to just verify when you're designing these filters, where you want to filter out these frequencies, you want to just verify that whether it is able to reject components which are in these frequency ranges which correspond to wave frequencies. So rather than having a very accurate model of the ship and then precisely figuring out what the motions are, I can just use a second order filter to simulate those motions and test my observers. I need not go through the process of actually modeling the entire thing because it's not really very relevant from a practical standpoint. All that effort will be wasted. Because at the end of the day, I just want to remove those frequencies. That is what is of our interest. And you'll see that when I'm now talking about the filters, that is what will happen. Let's see that. Okay, so our so-called total output is composed of, we are assuming that it is composed of some low frequency stuff and wave frequency stuff. And our target here is to get an estimate for psi, right? Whenever I put a hat, I mean that I want to estimate that variable. I actually am measuring y, but I want to estimate what is psi of t. Okay, the idea is we will take this y of t, pass it through a second order filter such that we eliminate all the frequencies in the wave frequency regime, and what should come out should more or less represent our system which we want to look at. All right, the simplest of the ways to do that is to pass it through some sort of a low pass filter, and the simplest of that is what we call as a first order low pass filter. Okay, what this is doing, this is basically saying that wherever the frequencies are over the value of 1 by TF, those frequencies I'll eliminate. Now, let's try to understand what is going on here. If I were to plot this transfer function, substitute S is equal to I omega, okay, and make a plot of it, what happens as omega keeps increasing? The value of this transfer function is decreasing or increasing?
It will decrease.
It will decrease, right? It will be 1 by TF times I times omega plus 1. This is what it is, whose absolute value I'm interested in. As omega increases, this fellow's value is going to decrease. Right? Now, in fact, 1 second. Its value will be 1 by 1 plus omega square TF square. When omega is 0, what will be this fellow's value?
1.
It will be 1. So it starts off at 1, right? And I'm only interested in the absolute value of this transfer function. So I'm basically looking at absolute value of it, okay? And when omega goes to very high, it goes to 0, correct? Everybody with me so far?
Yes, sir.
Yes, sir.
So how does this go? How does this graph look like? It will look like somewhat like a something like that. Correct? It's starting at 1, going to 0. And you will see that anything which is where the omega is less than 1 by TF, okay? When omega is less than 1 by TF, this value or which means omega TF is less than 1. This value will be pretty close to 1. Okay. In essence, what that means is that this curve doesn't look like the way I have drawn it, but it will look something like that, where the drop off will really start at 1 by TF. Because beyond 1 by TF, omega times TF is really becoming larger. Up till then, it is comparable to 1. Right? So in that frequency range, between 0 to 1 by TF, whatever frequencies I give as an input to the filter, it returns back the same frequencies with similar amplitude, more or less. That's what you're seeing here, right? That is the value which is 1. So if I give a unit amplitude as an input, I should see an output also which is of unit amplitude, close to unit amplitude. Not precisely, close to unit amplitude. But the moment I give a input of a higher frequency, you will see that the output amplitude from the filter will be very, very low. Okay, so what am I doing now? I am basically passing whatever the measurement inputs have come in terms of the compass heading measurements, let us say. I am passing it through this filter, and then what will happen? Whatever is the low frequency component of that signal will be preserved, but the higher frequency components will be attenuated. Is that making sense for everyone?
Yes, sir.
Okay, so whenever higher frequency signals are given as an input, it will not be passing through, or I'll be kind of attenuating those values out. So as long as I can put my 1 by TF to be in such a location that it is lesser than all the wave frequencies, then my job is done. If all the wave frequencies lie to the right side of 1 by TF, when I pass through the filter, those frequencies will get attenuated, right? Still seeing some confusion. Anand?
Yes, sir.
Got it? Aditya?
Yes, sir.
Got it?
Yes.
So the simple idea is, as long as I can choose 1 by TF to be sufficiently to the left hand side of all the wave frequencies, I can eliminate all those components and they will basically be much smaller in the output signal which I get. Okay, so that basically can then become my estimated value, which I am simply passing it through a filter.
Sir, I'm still a little bit confused. Like, why do we need to then separate the Y of S into two frequencies, the lower and the wave frequency?
I was only representing it, Aditya, here.
Y of S is still having both frequencies, right? Low frequency.
Y of S will have both frequencies, correct?
The low frequency and the wave frequency. Then we are just passing this through a low pass filter to filter.
The point is precisely that I am just passing it through a low pass filter to eliminate whatever is on the other side. Now the question is, instead of what is that other component, that wave frequency component, what is it? If I have to mathematically write, I can either write it in a very complex manner as wave elevation and so it is coming, or I can simply say it is coming through some second order filter. My point is I'm going to eliminate it anyway, so I really do not care how I model it.
So we can approximately model it instead of doing it accurately.
Correct. So when you are designing your so-called observer, where you want to tune your filter, you only need a rough rough estimate of how the yaw angle would look in a wave C state. You don't need an exact time history of what the waves will cause your yaw angle to be. You just need some response in those frequencies which corresponds to the wave frequencies. That you can get by simulating it in a second order filter. That is the idea.
So basically, using this approximation, we are just getting which frequencies we need to eliminate, more or less which frequencies we have to eliminate, and that we are doing using that low pass filter.
No. Okay. Maybe I'm not being very explicitly clear here. See, in the real field, you don't need to model this at all because that is anyway coming directly as a part of the environment. If you're on board the vessel and you're standing there, your ship is automatically responding to the waves.
Yes.
This is in terms of the design process. So when I'm trying to design my low pass filter, okay, at that time I need to know that where should I put my cutoff frequency, where should 1 by TF be,
Yeah.
right? And 1 by TF should definitely be on the left side of the wave frequencies of interest.
Yes.
And if I wanted to try to simulate that system in a computer to verify that my filter is doing what it is supposed to do, I need some model for those wave frequencies.
Yes. Yes.
That rather than getting it through a precise modeling approach, I'll get it through this second order filter. That's all I'm saying. Now, when you go to the real field, you're not modeling at all because environment, the nature is at play there. Nature is already giving you those signals. There is no need to model them anymore. But for our testing purposes, if you want to test that in the labs, then we can model it using a second order filter and get away with it. I need not go for a very accurate high fidelity modeling. A low fidelity second order filter will do the job to give me some signal which representatively looks something like a yaw angle, which I would really see in an ocean.
Yes.
That is all I was saying. We are not using that modeling in the design, we are not using that modeling per se in the
Yeah.
the filter is not using that.
My doubt was the same. Like I thought, like that 1 by TF value that we are using, we are getting it from this modeling.
No. If you want to verify that the filter is doing its job or not, for simulation purposes, you have to do that second order filter to simulate the motions of the yaw angle in the waves.
Okay.
Still not confusion. Confusion still is there, or is it
A bit clear now, but I want to like I will read this again and
No,
see
I'm
this.
talking about everyone. I'm not just talking about you. See, the filter when I design, I want to make sure all those frequencies in the wave components are eliminated. Okay, so suppose I chose TF as 0.1 or say I chose TF as 1. So everything which is higher than 1 second is getting eliminated. That doesn't serve my purpose if the wave is at 5 seconds, right? If I know that the wave frequency region is between say 5 seconds to 20 seconds, let us say, okay, then the lowest wave frequency of the wave will be corresponding to 2 pi by 20, okay, which is about 0.3 radians per second. So as long as my 1 by TF value or 2 pi by TF, when I say 1 by TF, I'm really referring it to in hertz. Okay, so if my 2 pi by TF value is less than 0.3 hertz, 0.3 radians per second, then I know for a fact that all the wave frequencies will be attenuated. But after I design my filter, I want to test it. That okay, I chose the 1 by TF at a particular value, but how does it look? How does the time series look like? What the filtered time series versus the actual time series, how does it look like? In order to do that, I need to simulate the process. For that simulation process, rather than use the RAOs and get a very precise value of yaw, I can simply tune a second order filter to give me some approximate values, which looks something like what the ship would yaw. And then I can benchmark my performance and see whether those components are getting attenuated or not. As simple as that. We are not using the second order wave formulation part in the design of the filter. We are only using it to evaluate the performance of our filter. Is that making sense? Okay.
Then the design, what was our we tested it with the that second order one, but what did we design it with then?
1 by TF is what you are designing it. The TF value is what you are choosing, and that is to choose appropriately.
But indirectly, we are actually using that thing only to, like, if we say choose it wrongly, that OTF value, then we are actually, then we see that it is with the second order one, it was not doing, like, it was not actually removing them. So we need, we know that we need to change TF.
So you come back and you change TF and see whether it has reduced sufficiently or not.
But then it is kind of directly, indirectly, we are using the same thing to design the TF, right?
What are we using to design?
Like the second order one.
Okay. It's like a chicken and egg problem. Yes, you are using it, but my point is, from a design perspective, you're not using the, what you call, the response which you're getting. You're not using that to change your TF. You're looking at it and changing the TF manually. It is not as if the amplitude there is kind of feeding back into your design.
Okay. We have already set the TF.
You are setting a TF and observing what is happening, whether you are satisfied with it or not. Now, Vallabh may be satisfied, Aditya may not be satisfied with the same filter. He may say, no, I need to shift it further left. Right? For the same second order filter, you may be saying, okay, 0.3 radians per second is good enough. He may say, no, I want 0.03 radians per second. Right? And both of you would be right.
Yeah, both of them would actually remove the wave ones.
His one would remove more.
Yeah, more actually.
Right. So where he is saying that the threshold that I am acceptable to me is far lower than what is acceptable to Vallabh. So it is only from that perspective, for an evaluation perspective, it is useful, but it's not really being used in the design. It's for performance metric evaluation only you are using it. I hope that differentiation is clear.
Yes.
Okay, so that second order modeling of the wave component of it is only used for evaluating these filters. That's all. We are not using it in the design anywhere. Okay, so this is the simplest of the first order. Sorry, was there a question?
So, like, if we are doing all of this, like, beforehand only, so we could actually use some data also, right? Actual data also we could use. We don't need to model it then.
Yes, you could use actual data if you have it available. So, for example, let us say you have built one ship which is operating at a particular location, doing its dynamic positioning and doing its thing. Okay, now you are designing a sister vessel for it. Okay, which has similar characteristics as the original one. Then you can assume that whatever was measured with the first fellow, you can use that as an input to the system to evaluate whether your filter is working properly or not. You can absolutely use it.
Yes.
Okay, you can in fact, even after you have built it, you can take it to the field and do a test also, where also you will not need to model it anymore, because wherever the environment is giving it to you, you need not model it, right? So for example, let us say when I am designing an assignment for you to look at guidance and control, I have to model the dynamics of the craft because it is being simulated here. So that's why I have to program the dynamics. But suppose I told you, you build your guidance and control algorithm and we'll evaluate it in the field, then I need not model the dynamics of the craft. It's naturally going to happen in the field, right? It's as simple as that. I hope that is making sense.
Yes, sir. Yes.
Then I need not model it. The modeling is for our benefit. So that if you want to test it on our systems before we go for a field deployment, because field deployment is more expensive. You don't want to do field deployments every now and then. It takes a lot of effort. See, for example, the experiment that you want to do. So much planning has to be done beforehand before you can take it to the lake, isn't it? Every time if I wanted to made a small change in TF, to evaluate it, I have to plan 1 week of experiments to go and see. Doesn't make sense, right?
Yes.
At that point, a modeling would be very useful for you. To just see representatively how good it is or how bad it is. So the modeling part is only used for verifying whether the design is for our benefit, to see whether the design is doing what it is supposed to do or not. Okay, shall we proceed further?
Yes, sir.
I want to complete this, at least this first order filtering process. Okay, now this first order filter really works well only when there is a caveat to it. Okay, it only works well when the filter's frequency is sitting to the left side of the interest of wave frequencies. Correct? But there is also a second caveat, that the bandwidth of the original system, of the controlled system, should be much shorter than the filtered signal. Okay, what do I mean by that? If my closed loop system's dynamics is looking like that, and I design a filter here, okay, so let us say that the black line is my system transfer function, and let's say I'll draw it in red, my filter looks like this. Now when I do the controller, when I've tuned my controller to do its duty, so what does it mean? I ask the controller to take care of whatever is happening in here. I want that to be passed in my controller. That's what I have said. But then my filter is kind of clipping me, right? It's saying that some frequencies of interest which you are interested in controlling, I'll not let them pass. And that becomes a problem. So therefore, you want to make sure that the control bandwidth of your closed loop system is at least to the left side of the filter's frequency, and the wave frequencies lie further to the right side of the filter's frequency. Okay, so you want, so in the case where there is a clear demarcation as to where the omega b and omega e, the encounter frequency of the waves, so this is encounter frequency, okay, of the waves, is far separated from where the control bandwidth is operating, then you can choose a filter nicely in between somewhere, so that all the dynamics is still preserved. And that happens naturally for very large ships. So if you look at a large oil tankers and things like that, you will naturally see this happen, that there is a large demarcation between what is the control bandwidth of the closed loop system and where are the wave frequencies located. They'll be very far apart. It is very obvious, right? Because the inertia of these vehicles will be so large that they won't respond very quickly. So whatever they will respond is far in the low frequency regime. And all the wave frequency stuff is happening at a much higher frequencies, and there's a clear demarcation between the two. But the moment my ship becomes smaller, my inertia of the vessel is lower, which means now it is much more response. It is more prone to response. It may so happen my control bandwidth is actually exceeding into the wave frequency regime, in which case I can't use a low pass filter to get the job done, right? Because then I'll be eliminating some more stuff. So in that case, you have to be a little more cleverer about it. Okay, and at that time we will look at what is called as a cascaded notch filter. And I'm going to discuss about the notch filter in the next class. Okay, so but for most considerations, please understand for very large ships, this separation between omega b and omega e is large enough. So therefore, we can actually go ahead and do the filter design properly. We can choose a filter cutoff frequency somewhere in between these two, and it will be sufficient enough for our purposes. But when it comes to the smaller vessels, since omega b can then be closer to omega e, then it becomes a challenge, in which case we use what are called cascaded notch filters, and we'll discuss about them in the next class. However, you will see that the story is not all romantic there, in the sense that you have to give up something in order to make that happen, because there is an overlap between your control bandwidth and your wave frequency regime. That overlap region will always be a problematic region for control. We'll discuss about it in the next class. Okay, but let me maybe just finish this part off so that we can come to a logical conclusion here before we leave off today. So what we looked at is a first order low pass filter, which is given by this transfer function which you have seen here. But I can make this attenuation, the way it is dropping off, I can play around with it as well. I can make it drop off much faster or much more slower by what are called as Butterworth filters. So instead of having a first order filter, now I'll look at a second order, third order, fourth order filters in order to make sure that that attenuation is much more. Okay, so let me show you what I mean by that. So a Butterworth filter is given by 1 by some polynomial value, and that polynomial is basically found by solving this system. P of s times P of minus s is 1 plus s by j times omega f to the power 2n, where n is the order of the filter. So if I'm choosing a n as 2, then I'll find out what is the P of s, and once I find the P of s, 1 by P of s will become my low pass filter. So let me show you what those functional form looks like. There's no point in deriving these are results which are directly available. So we'll just state them and go forward. So for n equal to 1, we saw that this is the case, right? Where omega f is basically taken as 1 by tf in this particular case. Okay. Now when n is equal to 2, the transfer function starts to look like a second order system, like a spring mass damper system, which you have seen before. But the one which will satisfy this Butterworth frequency, turns out this zeta value will come out to be sine of 45 degrees. Okay, so that becomes your Butterworth filter of second order. Similarly, you can define a Butterworth filter of third order, which will come out to be this way, where this zeta value turns out to be sine of 30 degrees. Okay. Basically, what we are doing is you're trying to find the polynomial which satisfies this system. You're trying to see which P of s satisfies this system. Okay. And then we are basically saying that this low pass filter which I have got will now try to attenuate. So if I plot all of them for a same value of omega f, you'll see that n equal to 1, the low pass filter does the attenuation at a much moderate rate, but the higher order filters are attenuating the signals at a much faster rate. The rate is much higher, so the amplitude really gets decayed much more quickly. So then one might wonder, why not just go for the fourth order filter? Why do you bother teaching us about the first order filter? The reason is you gain something, you lose something. What you lose is the phase. See what is happening to the phase? You're now starting to see that within this omega f range, which is of interest, to this side is of interest, there is a much more phase difference for the fourth order filter compared to the first order filter. Which means that if the input signal is given as a sinusoidal value, there is very little phase difference in what comes out when I use a first order filter. But when I use a higher order filter, I'm actually starting to see a phase difference come into the picture. And the phase difference is more at the higher frequencies and less at the lower frequencies. But nevertheless, that phase difference is there. So the signal that you are getting back, the so-called eta hat, is not exactly equal to that eta in reality. It's not really what is the low frequency component. It's not exactly equal to that because there is some phase lag between them, especially at the higher frequency components, which are closer to the cutoff frequency. So even though the attenuation is better with a higher order filter, you are not seeing a change in phase for the lower order filters, whereas for the higher order filters, you are seeing a significant change in phase. And that is something you have to live with, basically, a compromise between the two of them as to where I should draw the line. Everybody following me so far? So far, our discussion has been limited to the application of low-pass filters where there is a separation between the bandwidth of the control system and the wave frequency regime. There is a clear distinction between them, and we are choosing our filters cutoff frequency in between these two. Okay. In the next class, we'll talk about cascaded notch filters, where you'll see that where there is an overlap, how do I deal with those problems? In that case, we'll need a band pass filter of sorts. And we will see how to design those band pass filters using what are called as notch filters. Okay. So the idea here is now if I pass a raw compass measurements, which I am getting from my measurements through this low pass filter, it will attenuate all the wave frequency components, and what will be left out will be the so-called low frequency components. The lower the order of the filter, the more real what is happening in the field I am seeing in the signal as well. The higher the order of the filter, I am seeing the, yes, I'm attenuating the other components, but I'm incurring a phase lag, which means that there is a delay of sorts. And that's not quite good for our systems. We want it to be representatively close by, right? So in that sense, you win some and you lose some, and an effective compromise has to be made when you're designing these low-pass filters. We'll stop right here. We'll pick it up tomorrow, where we'll continue further. Okay. I know we have overshot time today, but I wanted to cover the aspects of RAOs which was not very clear in a concise manner. Okay, let me stop recording.